Picture this, a vast cosmic dance, millions of stars swirling together in clusters, hiding secrets that defy our understanding of the universe. These stellar gatherings are not just beautiful to behold, they are filled with mysteries that challenge even the brightest minds in astronomy. What if I told you that some of these star clusters harbor phenomena so strange, they seem almost otherworldly? From stars that refuse to age to ghostly remnants of ancient explosions, the universe has packed these clusters with surprises that leave us in awe. Today, we're diving into 50 of the most bizarre and mind-bending discoveries about star clusters, each one a reminder of how much we still have to learn about the cosmos. So, buckle up and join me on this journey into the unknown, where every discovery is a step closer to unraveling the mysteries of the universe. Let's explore these cosmic enigmas together. Trust me, you won't want to miss what's coming next. Now turning to our first discovery, we find ourselves gazing at the Beehive Cluster, also known as Messier 44. Nestled within this bustling gathering of stars lies a puzzling mystery, a vast, empty region that defies explanation. This void stretching across the cluster is not just a simple gap, it's a cosmic anomaly that has left astronomers scratching their heads. How could such a dense star cluster have a space so devoid of stars? Theories abound, with some suggesting it could be the result of a massive stellar ejection, where stars were flung out of the cluster by gravitational interactions. Others propose it might be the remnants of a collision with another cluster, leaving behind a ghostly scar. What makes this void even more intriguing is its sheer size. It's large enough to stand out even in a cluster teeming with stars. Astronomers are still piecing together the clues, but one thing is certain. This mysterious void in the Beehive Cluster is a reminder that even in the most familiar corners of the universe, surprises await. As we shift our gaze to another fascinating corner of the cosmos, let's explore the star cluster Messier 67. This cluster, often referred to as the King of Clusters for its richness and diversity, holds a peculiar secret. Some of its stars seem to have discovered the cosmic fountain of youth. These stars, known as rejuvenated stars, appear significantly younger than their actual age, defying our understanding of stellar evolution. Normally, stars follow a predictable life cycle, growing older and dimmer as they exhaust their fuel. But in Messier 67, some stars have seemingly reversed this process, shining brighter and bluer as if they've been given a second lease on life. How is this possible? The leading theories point to two intriguing mechanisms: mass transfer and stellar mergers. In the case of mass transfer, a star might siphon material from a nearby companion, reigniting its core and altering its appearance. Alternatively, two stars could collide and merge, combining their energy and creating what appears to be a younger, more vibrant star. This phenomenon of stellar rejuvenation challenges our assumptions about how stars evolve and offers a glimpse into the dynamic and sometimes chaotic nature of star clusters. Messier 67 reminds us that even the universe's oldest inhabitants can surprise us with their ability to change and adapt. Now shifting our focus to another marvel in the night sky, let's take a closer look at the twin clusters in Perseus known as H and Chi Persei. These two star clusters, often referred to as the double cluster, are a breathtaking sight through a telescope and have captivated astronomers for centuries. Located about 7,000 light-years away from Earth, they sit relatively close to each other in space, creating a striking pair that appears side by side in the sky. What makes these clusters particularly fascinating is their shared history. Both H and Chi Persei are believed to have formed around the same time, roughly 13 million years ago, from the same massive cloud of gas and dust. This makes them not just neighbors but siblings in the cosmic sense. Despite their similar origins, each cluster has its own unique characteristics. H Persei is slightly richer in stars, while Chi Persei contains more massive, luminous stars. Astronomers often study them together because they provide a unique opportunity to compare how star clusters evolve under similar conditions. By examining these twins, scientists can gain insights into the processes that shape star clusters, from their birth in turbulent gas clouds to their eventual dispersal into the galaxy. The twin clusters remind us that even in the vastness of space, connections and relationships can reveal profound truths about the universe. Now exploring another cosmic wonder, let's dive into the fast-moving stars of the Pleiades cluster. Known as the Seven Sisters, this star cluster is not only one of the most recognizable in the night sky, but also home to some of the most intriguing stellar phenomena. Among its hundreds of stars, astronomers have discovered a handful that are racing through space at unusually high speeds. These runaway stars didn't start their journey this way. Instead, they were likely ejected from the cluster due to intense gravitational interactions. Imagine a cosmic game of billiards where stars pass close to one another, and the gravitational pull sends one shooting off at incredible velocity. In some cases, these interactions involve binary star systems where two stars orbit each other. If a third star gets too close, it can disrupt the system, flinging one of the stars away at high speed. The presence of these fast-moving stars tells us a lot about the Pleiades' internal dynamics. It reveals that the cluster is a hotbed of gravitational activity, with stars constantly influencing each other's path. This chaotic environment helps astronomers understand how star clusters evolve over time, as stars are gradually lost to the surrounding galaxy. The Pleiades, with its blend of beauty and mystery, continues to offer clues about the forces that shape the universe. Now shifting our focus, let's explore the hidden role of dark matter in the Hyades cluster. This nearby star cluster, often referred to as the V-shaped cluster in the Taurus constellation, has long been a subject of fascination. But what's truly intriguing is the discovery that dark matter may be influencing its structure and movement. Astronomers have detected subtle gravitational effects within the Hyades that can't be explained by the visible stars alone. These anomalies suggest the presence of dark matter, an invisible substance that makes up a significant portion of the universe's mass. By studying the motions of the stars in the cluster, researchers noticed that some stars were moving in ways that couldn't be accounted for by the gravity of the visible matter. This led them to infer that dark matter must be playing a role, even in a relatively small and nearby cluster like the Hyades. This discovery challenges our understanding of star clusters, as it suggests that dark matter isn't just confined to larger structures like galaxies or galaxy clusters. It also raises questions about how dark matter interacts with ordinary matter on smaller scales. The presence of dark matter in the Hyades could help explain why some star clusters remain bound together for billions of years, despite the gravitational forces that might otherwise tear them apart. As we continue to unravel the mysteries of dark matter, the Hyades cluster offers a unique laboratory for studying its influence on the universe's smaller cosmic neighborhoods. Now shifting our gaze to the vastness of Omega Centauri, we uncover a fascinating anomaly that has left astronomers scratching their heads: the unusual binary star systems nestled within this massive globular cluster. Binary stars, where two stars orbit a common center of mass, are common in the cosmos, but the ones found in Omega Centauri are anything but ordinary. These systems defy our expectations of how stars evolve and interact in dense stellar environments. Typically, in such crowded clusters, the gravitational forces between stars are so intense that binary systems are either disrupted or prevented from forming in the first place. Yet, Omega Centauri boasts a surprising number of these paired stars, some of which are incredibly close together, completing their orbits in just a few hours. This raises a pressing question: how do these binary systems survive or form in such a chaotic environment? One theory suggests that these systems might be the result of stellar collisions or close encounters, where stars are literally forced into partnerships by the cluster's gravitational dance. Another possibility is that these binaries formed much earlier in the cluster's history, before it became as densely packed as it is today. What's even more intriguing is that these binary systems could play a crucial role in shaping the cluster's dynamics. Their gravitational interactions might help stabilize the cluster, preventing it from falling apart over time. This discovery challenges our understanding of stellar evolution, particularly in extreme environments like Omega Centauri. It also opens up new avenues for studying how stars form and interact in the most crowded corners of the universe. As we continue to explore these unusual systems, Omega Centauri remains a treasure trove of cosmic mysteries, offering clues to the complex and dynamic processes that govern the life cycles of stars. Now shifting our focus to the Coma star cluster, we encounter a cosmic enigma that defies expectations: the presence of ghostly remnants of gas lingering within this ancient stellar gathering. As one of the oldest known star clusters, the Coma cluster is a place where stars have long since settled into a quiet, mature phase of their existence. Yet astronomers have detected faint traces of gas, a discovery that raises intriguing questions. Typically, in clusters of this age, gas is believed to have been expelled long ago, either blown away by stellar winds or consumed in the process of star formation. So, how did this gas manage to persist? One possibility is that the gas is a relic from the cluster's early days, somehow surviving the tumultuous processes that usually strip clusters of their interstellar material. Another theory suggests that the gas might have been replenished, perhaps by the slow evaporation of gas from aging stars, or even by the occasional capture of gas from outside the cluster. This unexpected finding challenges our understanding of how star clusters evolve over time. It also opens up new avenues for research, as the presence of gas could influence the cluster's dynamics and even provide the raw material for the formation of new stars. The Coma star cluster, with its ghostly gas, reminds us that even in the oldest corners of the universe, there are still mysteries waiting to be uncovered. Now turning to the Hercules cluster, known as M13, we encounter a star that defies the odds, a survivor of a supernova explosion. Supernovae are among the most violent events in the universe, typically obliterating the star at their core. Yet, this star in M13 somehow endured the catastrophic blast, offering a unique glimpse into the resilience of stellar bodies. So, how did it survive? One explanation is that the star was part of a binary system. When its companion star went supernova, the explosion ejected material outward, while the surviving star remained intact, now traveling at an incredible speed. This phenomenon, known as a runaway star, demonstrates the complex dynamics within star clusters. Another possibility is that the star was on the outskirts of the supernova's impact zone, shielding it from the full force of the blast. This discovery challenges our understanding of supernova and their effects on neighboring stars. It also highlights the incredible durability of some stellar objects, even in the face of cosmic chaos. The supernova survivor in M13 reminds us that stars, much like the universe itself, are full of surprises, pushing the boundaries of what we thought was possible. Now shifting our focus to the M4 cluster, we uncover an astonishing discovery: a white dwarf with a core resembling a diamond. White dwarfs are the dense remnants of stars that have exhausted their nuclear fuel, and while they are often studied for their end-stage properties, this particular white dwarf in M4 stands out for its extraordinary core. So, how did this diamond-like structure form? The immense pressure within the white dwarf's core compresses carbon atoms into a crystalline lattice, similar to how diamonds are formed deep within Earth. This process occurs as the star cools over billions of years, transforming its core into a cosmic gem. The discovery of this diamond core not only fascinates astronomers but also provides insights into the extreme conditions within white dwarfs. It challenges us to rethink the life cycle of stars and the unexpected treasures they leave behind. This phenomenon reminds us that even in the final stages of stellar existence, stars can produce marvels that captivate our imagination and deepen our understanding of the cosmos. Now uncovering another cosmic mystery, we turn our attention to NGC 6791, a star cluster that puzzles astronomers with its curious lack of red giants. Red giants, the late-stage evolution of stars, should be abundant in older clusters like this one, yet NGC 6791 defies expectations. So, where have these red giants gone? One possible explanation lies in the violent interactions within the cluster. Stars in dense environments like NGC 6791 often collide, disrupting their life cycles and preventing them from reaching the red giant phase. Another theory suggests that unusual evolutionary paths, perhaps influenced by the cluster's unique conditions, could cause stars to bypass this stage altogether. The absence of red giants challenges our understanding of stellar evolution and highlights the dynamic and sometimes chaotic nature of star clusters. This discovery not only raises questions about the fate of stars, but also invites us to explore the hidden mechanisms that shape their existence. As we continue our journey through the cosmos, NGC 6791 reminds us that even the most familiar processes in the universe can hold unexpected surprises. Now shifting our gaze to the star cluster M30, we encounter a fascinating anomaly known as blue stragglers. These stars appear younger and hotter than their counterparts, defying the natural aging process expected in such an ancient cluster. Typically, stars in clusters like M30 evolve in predictable ways, growing cooler and dimmer over time. Yet, blue stragglers stand out as vibrant, energetic exceptions to this rule. So, how do these seemingly youthful stars exist in an old cluster? One leading theory points to stellar collisions. In the densely packed core of M30, stars occasionally crash into one another, merging their masses and reigniting their nuclear processes. This collision creates a star that burns hotter and brighter, mimicking the appearance of a younger star. Another explanation involves mass transfer between binary systems. In this scenario, one star in a binary pair siphons material from its companion, gaining enough mass to rejuvenate itself and become a blue straggler. These unusual stars challenge our understanding of stellar evolution, revealing the complex interactions that can occur within star clusters. M30's blue stragglers remind us that even in the depths of space, nature finds ways to surprise us, rewriting the rules we thought we knew. Now venturing into the Orion Nebula cluster, we uncover a truly cosmic mystery: rogue planets. These are planets that wander freely through space, unbound by the gravity of any star. Unlike the planets in our own solar system, which orbit the Sun, these rogue worlds drift alone in the vast expanse of the cluster. So, how do these solitary planets come to exist? One theory suggests they were once part of a planetary system, but were ejected due to gravitational interactions with nearby stars or massive objects. Another possibility is that they formed independently, just as stars do, collapsing from denser regions of gas and dust. The discovery of these rogue planets challenges our understanding of planetary formation and dynamics. They reveal that planetary systems can be far more chaotic and unpredictable than we once thought. Moreover, their presence hints at the possibility of countless such worlds scattered throughout the galaxy, some of which might even harbor conditions for life. The Orion Nebula cluster's rogue planets remind us that the universe is full of surprises, offering new questions and insights into the nature of planetary systems. With each discovery, we learn just how dynamic and diverse the cosmos truly is. Now shifting our gaze to another cosmic enigma, we turn our attention to NGC 288 and the strange radio signals emanating from its depths. Unlike the usual hum of starlight, these signals stand out as puzzling whispers in the vastness of space. Astronomers first detected these emissions while studying the cluster's structure, and their origin remains a tantalizing mystery. One leading theory points to pulsars, the rapidly spinning remnants of massive stars that emit beams of radio waves as they rotate. These cosmic lighthouses could be hidden within NGC 288, their signals reaching us across immense distances. Another possibility is the presence of black holes, particularly those lurking in the shadows of the cluster. As black holes interact with their surroundings, they can produce powerful bursts of radio energy, offering another potential explanation for these signals. Yet, what makes this discovery so intriguing is the challenge it poses to our understanding of star clusters. NGC 288 is not typically known for such energetic phenomena, making these radio waves an unexpected find. As scientists continue to investigate, they hope to uncover more about the hidden forces at work within this cluster. These enigmatic signals remind us that even in the quiet corners of the cosmos, there are secrets waiting to be unraveled. Each new discovery pushes the boundaries of what we know, inviting us to rethink the nature of these stellar gatherings. Now stepping into a different corner of the cosmos, we find ourselves drawn to the globular cluster M15, a dense gathering of ancient stars that holds a surprising secret at its core. Nestled within this cluster is a supermassive black hole, an object so massive and powerful that it defies our expectations of what globular clusters can harbor. For years, astronomers believed that such black holes were exclusive to the centers of galaxies, but the discovery of one in M15 has turned that assumption on its head. This colossal black hole, with a mass thousands of times greater than our Sun, raises questions about how these clusters form and evolve. Its presence suggests that globular clusters might have once been the cores of smaller galaxies that were stripped away over time, leaving behind these black holes as remnants of their former glory. Alternatively, it could point to a more violent history where runaway stellar collisions and mergers created these giants within the cluster itself. What makes this discovery even more puzzling is how it challenges our understanding of the dynamics within globular clusters. Such an immense gravitational force would have a profound impact on the stars surrounding it, yet M15 appears to function much like other clusters. This contradiction has left scientists grappling with new theories and models to explain how such a black hole could coexist with its stellar neighbors. As we continue to study M15 and its hidden powerhouse, we're reminded that the universe is full of surprises, each one pushing us to expand our knowledge and rethink what we thought we knew about the cosmos. Now shifting our gaze to another cosmic enigma, we arrive at the Tarantula Nebula Cluster, a vibrant and chaotic region of star formation that holds a peculiar mystery. Within this cluster, astronomers have observed stars that seem to vanish without a trace, defying our understanding of stellar behavior. These disappearing stars, once bright and visible, leave behind only questions and speculation. One leading theory suggests that these stars may have been consumed by black holes lurking within the cluster. If a black hole were to pass close enough to a star, its immense gravitational pull could swallow the star hole, leaving no visible remnant. Another possibility is that these stars collapsed into black holes themselves, a rare but plausible event for massive stars nearing the end of their life cycle. However, not all explanations point to such dramatic events. Some scientists argue that these disappearances could be the result of observational errors or limitations in our telescopes. The Tarantula Nebula Cluster is densely packed with stars, dust, and gas, making it challenging to track individual stars over time. A star that appears to vanish might simply be obscured by these dense clouds or have moved out of view. What makes this phenomenon even more intriguing is the possibility of entirely new astrophysical processes at play. Could these stars be undergoing transformations we've yet to understand, or might they be interacting with dark matter in ways that remain hidden from our instruments? As we continue to study the Tarantula Nebula Cluster, these disappearing stars serve as a reminder of how much we still have to learn about the cosmos. Each vanished star is a puzzle waiting to be solved, pushing us to refine our tools, challenge our assumptions, and explore the unknown with renewed curiosity. Now turning to another remarkable discovery, we venture into the Hyades cluster, a densely packed collection of stars near the heart of our galaxy. This cluster stands out not just for its staggering number of stars, but for the exotic chemistry that defines it. Within the Hyades cluster, astronomers have detected elements and compounds that are rarely found in such abundance elsewhere in the universe. Among these are heavy elements like iron and nickel, as well as complex molecules that hint at unusual processes at work. The extreme environment of the Hyades cluster plays a crucial role in shaping this unique chemistry. Located just a few dozen light-years from the supermassive black hole at the center of the Milky Way, the cluster is exposed to intense radiation, powerful magnetic fields, and immense gravitational forces. These conditions create a cosmic laboratory where atoms and molecules are constantly bombarded, leading to the formation of rare and exotic compounds. One theory suggests that the high-energy environment causes frequent collisions between atoms, forcing them to combine in ways that wouldn't occur under normal circumstances. Another possibility is that the cluster's proximity to the galactic center exposes it to streams of material ejected by the supermassive black hole, enriching it with unusual elements. What makes this discovery even more fascinating is its implications for our understanding of star formation and the chemical evolution of galaxies. The Hyades cluster provides a glimpse into how extreme conditions can shape the building blocks of the universe, offering clues about the origins of the elements that make up everything around us. As we continue to study this extraordinary cluster, its exotic chemistry reminds us of the incredible diversity and complexity of the cosmos, challenging us to rethink what we know about the processes that drive its evolution. Now shifting our gaze to another cosmic marvel, let's delve into the mysterious stellar streams flowing out of NGC 6397. This globular cluster, located in the constellation Ara, has captured the attention of astronomers for its peculiar behavior. Unlike most clusters where stars remain tightly bound, NGC 6397 is losing its stars in long, graceful streams that stretch across the night sky. These stellar streams are like cosmic rivers tracing the cluster's movement through the galaxy. But what causes stars to escape in such a dramatic fashion? The answer lies in the intense gravitational forces at play. As NGC 6397 orbits the Milky Way, it passes through regions of varying gravitational pull. This interaction, known as tidal stripping, gradually pulls stars away from the cluster, creating the streams we observe today. Think of it like a tree shedding leaves in the wind, except here it's stars being tugged away by the galaxy's tides. The discovery of these streams tells us a lot about the cluster's history and its interactions with the Milky Way. By studying their shape and trajectory, astronomers can piece together the cluster's past movements and even estimate its age. Interestingly, these streams also offer clues about the distribution of dark matter in our galaxy. As the cluster's stars are pulled apart, their paths are influenced by the unseen dark matter that permeates the Milky Way. This makes NGC 6397 not just a fascinating object of study, but also a valuable tool for understanding the invisible forces shaping our universe. As we continue to explore these stellar streams, they remind us of the dynamic and ever-changing nature of star clusters, offering a glimpse into the intricate dance between gravity and time. Now turning to one of the most puzzling phenomena in star clusters, we arrive at the mysterious X-ray sources detected in 47 Tucanae. This dense globular cluster, located in the constellation Tucana, has long fascinated astronomers. While it's known for its stunning array of stars, what really stands out are the strange X-ray emissions emanating from its core. Unlike the steady glow of visible light, these X-rays are erratic and intense, hinting at some of the most extreme objects in the universe. So, what's causing these emissions? The leading suspects are neutron stars and white dwarfs, two of the most exotic remnants of stellar evolution. Neutron stars, the collapsed cores of massive stars, are incredibly dense and can emit powerful bursts of X-rays, especially if they're part of a binary system. Similarly, white dwarfs, the final stage of smaller stars, can also produce X-rays if they're accreting material from a companion star. But here's the twist. 47 Tucanae has an unusually high number of these X-ray sources compared to other clusters. This has led astronomers to wonder if there's something unique about its environment that favors their formation or survival. One theory suggests that the cluster's densely packed core increases the chances of stellar interactions, such as collisions or close encounters, which could create or rejuvenate these X-ray emitting objects. Another possibility is that the cluster's age plays a role. At over 10 billion years old, 47 Tucanae has had ample time for stars to evolve into neutron stars or white dwarfs, making it a hotspot for such phenomena. Studying these X-ray sources not only sheds light on the cluster's history, but also helps us understand the behavior of these extreme objects across the cosmos. As we continue to unravel the secrets of 47 Tucanae, it serves as a reminder of the incredible diversity and complexity hidden within star clusters. Shifting our gaze to the realm of cosmic timekeeping, we arrive at M92, a globular cluster that holds a celestial treasure, the oldest known star in its population. Nestled in the constellation Hercules, M92 is a relic of the early universe, and this ancient star offers a glimpse into the dawn of stellar creation. Estimated to be over 13 billion years old, this star predates even the formation of many galaxies, including our own Milky Way. Its age is not just a number, it's a window into the conditions of the early universe when the first stars began to ignite. What makes this star so remarkable is its composition. It contains very few heavy elements, which astronomers refer to as metals. In the early universe, before multiple generations of stars had lived and died, the cosmos was dominated by hydrogen and helium, the simplest elements. This ancient star, therefore, is a pristine example of what the first stars might have looked like, untouched by the complex chemistry that would later arise from supernova and stellar winds. Studying it allows astronomers to piece together the story of how the universe evolved from a sea of simple elements to the diverse chemical landscape we see today. Its existence also raises intriguing questions about the formation of globular clusters themselves. How did such a cluster with its ancient stars form so early in the universe's history? And what does it tell us about the environments that allowed these stars to endure for billions of years? By unraveling the mysteries of this ancient star, we not only learn about M92, but also gain insights into the origins of the cosmos itself. It's a humbling reminder that some of the answers to our biggest questions about the universe are written in the light of its oldest inhabitants. Now diving into the darker side of cosmic behavior, we uncover the phenomenon of stellar cannibalism in the globular cluster NGC 1851. This cluster, located in the constellation Columba, presents a fascinating yet unsettling scenario: stars consuming one another. But how does this happen? In densely packed clusters like NGC 1851, stars often come dangerously close to each other due to the tight gravitational pull. When two stars pass too close, their gravitational interactions can result in one star tearing material away from the other or even fully absorbing it. This process, known as mass transfer, can dramatically alter the life cycle of both stars involved. The more massive star grows even larger, while the smaller star may be left as a mere remnant stripped of its outer layers. But the implications of stellar cannibalism go beyond the fate of individual stars. It provides crucial insights into the evolution of star clusters themselves. By studying these events, astronomers can better understand how clusters age and why certain stars appear more massive or luminous than expected. NGC 1851, with its high density and frequent stellar interactions, serves as a cosmic laboratory for observing these extreme behaviors. What's even more intriguing is the role this plays in the formation of exotic objects like blue stragglers or even black holes. Stellar cannibalism can lead to the creation of stars that defy conventional evolutionary models, offering clues about the dynamic and often violent processes that shape the cosmos. As we unravel the mysteries of NGC 1851, we're reminded that the universe, for all its beauty, is also a place of fierce competition and survival, where even stars are not immune to the forces that drive them. Now shifting our gaze to another marvel of the cosmos, we explore the curious alignment of stars within the Butterfly Cluster, also known as M6. This open cluster, located in the constellation Scorpius, earned its name from the graceful arrangement of its stars resembling the wings of a butterfly. But what makes this cluster truly fascinating is the unexpected alignment of its stars, a phenomenon that continues to puzzle astronomers. Typically, stars in a cluster are thought to move in random directions, influenced by their individual orbits and gravitational interactions. Yet in M6, a significant number of stars appear to move in a synchronized pattern, creating a striking alignment that defies the norm. One theory suggests that magnetic fields within the cluster could be responsible for this unusual behavior. As stars form, they are embedded in a cloud of gas and dust that often carries magnetic fields. These fields could influence the motion of the stars, guiding them into aligned paths over time. Another possibility is the role of tidal forces exerted by the galaxy itself. As the cluster orbits the Milky Way, the gravitational pull of our galaxy's massive structure could stretch and shape the cluster, causing its stars to align in a particular direction. This phenomenon isn't just a cosmic curiosity. It offers valuable insights into the dynamics of star clusters and the forces that shape them. By studying M6, astronomers can better understand how clusters evolve and how external influences, like magnetic fields and tidal forces, can leave their mark on these stellar communities. The Butterfly Cluster, with its delicate beauty and mysterious alignment, reminds us that even in the vastness of space, patterns and order can emerge from chaos, inviting us to uncover the secrets of the universe one star at a time. Now turning to another cosmic enigma, we delve into the mysterious glow surrounding the Carina Nebula cluster. This stunning region, located in the southern constellation Carina, is one of the most luminous and active star-forming areas in our galaxy. Its breathtaking beauty is complemented by an unexplained glow that has captured the attention of astronomers worldwide. What could be causing this persistent radiance? One leading theory points to ionized gas. Within the nebula, intense ultraviolet radiation from newly formed stars heats the surrounding hydrogen gas, causing it to emit a soft, ethereal light. This process, known as fluorescence, is common in star-forming regions, but the glow in the Carina Nebula seems unusually bright and widespread, hinting at an even more intense source of energy. Another possibility involves hidden stars. The nebula is home to numerous massive stars, some of which may be obscured by thick clouds of dust and gas. These hidden giants could be emitting powerful radiation that illuminates the surrounding material, contributing to the glow. Additionally, the presence of stellar winds and supernova remnants in the area could be playing a role. As these phenomena interact with the nebula's gas, they may produce shock waves that further energize the material, enhancing its luminosity. This mysterious glow isn't just a visual spectacle. It provides valuable clues about the processes shaping the nebula and the life cycle of stars. By studying the Carina Nebula cluster, astronomers can gain deeper insights into how stars form, evolve, and influence their surroundings. The glow serves as a cosmic beacon, guiding us toward a better understanding of the dynamic and ever-changing nature of star clusters. Shifting our gaze to the Hyades cluster, we uncover a fascinating phenomenon: runaway stars. these celestial wanderers have somehow escaped the gravitational pull of their birthplace, venturing out into the vastness of space. But how do stars manage to break free from a cluster as tightly bound as the Hyades? One leading explanation involves stellar encounters. In densely populated clusters, stars often come close to one another, and during these close encounters, gravitational interactions can fling stars out at high speeds. Another possibility involves binary star systems. If one star in a binary pair explodes as a supernova, the sudden loss of mass can send the surviving companion hurtling away at incredible velocities. Additionally, external forces such as gravitational interactions with nearby star clusters or even the Milky Way's galactic tide could play a role in ejecting stars from the Hyades. The discovery of these runaway stars isn't just a curiosity. It provides valuable insights into the dynamics of star clusters. By studying their paths and velocities, astronomers can piece together the history of the Hyades and understand the forces that shape its evolution. These stellar escapees serve as cosmic messengers, offering clues about the complex interplay of gravity, motion, and time within star clusters. Their journeys remind us that even in the seemingly stable realm of space, change is a constant. Now turning to Omega Centauri, one of the most massive and intriguing globular clusters in our galaxy, we uncover a curious anomaly: the unusual rotation of its core. Unlike many globular clusters that exhibit a more uniform or slower rotation, Omega Centauri's core spins at a surprising rate. This rapid and complex rotation has left astronomers puzzled, raising questions about how such a pattern could have formed. One leading theory suggests that Omega Centauri may have once been the core of a dwarf galaxy that was absorbed by the Milky Way. The remnants of this galactic merger could explain the distinct rotational behavior we observe today. Another possibility is that interactions with nearby clusters or the gravitational influence of the Milky Way itself have stirred the core over billions of years, creating the unusual spin patterns. The rotation of Omega Centauri's core isn't just a fascinating detail. It provides crucial clues about the cluster's origins and evolution. By studying these rotational dynamics, astronomers can piece together the history of how Omega Centauri formed and how it has interacted with its cosmic surroundings. This discovery also sheds light on the broader processes that shape globular clusters, offering insights into the forces that govern their structure and behavior. The unusual rotation of Omega Centauri's core serves as a reminder of the complex and dynamic nature of these ancient stellar systems, inviting us to delve deeper into their mysteries. As we continue to explore, each new finding brings us closer to understanding the intricate dance of stars, gravity, and time that defines the cosmos. Shifting our gaze to the Fornax cluster, we encounter a mystery that defies our understanding of the cosmos: the puzzling absence of dark matter. Dark matter, the invisible substance that makes up a significant portion of the universe's mass, is typically abundant in galaxy clusters, shaping their structure and gravitational pull. Yet in Fornax, this enigmatic material seems to be missing, leaving astronomers scratching their heads. One theory suggests that tidal stripping, a process where gravitational forces from nearby clusters or galaxies pull away dark matter, could be responsible. Over billions of years, such interactions might have stripped Fornax of its dark matter, leaving it unusually light. Another possibility is that observational errors or limitations have led to an incomplete picture of the cluster's dark matter distribution. Advanced telescopes and more precise measurements may eventually reveal hidden pockets of dark matter that current technology cannot detect. The absence of dark matter in Fornax challenges our understanding of how galaxy clusters form and evolve, prompting scientists to reconsider their models of cosmic structure. This discovery also raises broader questions about the nature of dark matter itself. Could it behave differently in certain environments, or are there other forces at play that we have yet to uncover? The Fornax cluster serves as a cosmic puzzle, reminding us that even our most fundamental assumptions about the universe are subject to change as new discoveries emerge. By continuing to investigate this anomaly, astronomers hope to shed light not only on fornax but also on the mysterious role dark matter plays in shaping the cosmos. Now venturing into the realm of theoretical astrophysics, we arrive at the Hercules cluster, also known as M13, where scientists speculate the existence of cosmic strings, hypothetical, one-dimensional defects in the fabric of spacetime. These cosmic strings, predicted by certain theories of the early universe, are thought to have formed during the rapid cooling phase following the Big Bang, leaving behind incredibly thin, yet extraordinarily dense filaments of energy. If they exist, cosmic strings in M13 could provide a unique window into the universe's earliest moments, offering clues about the fundamental forces that shape the cosmos. Detecting these strings, however, is no simple task. One method involves observing the gravitational lensing effects they might produce. As light from distant stars or galaxies passes near a cosmic string, its path could be bent or distorted, creating multiple images or a characteristic pattern in the light. Another potential detection method relies on the gravitational waves that cosmic strings might emit. These ripples in space-time, caused by the vibrations or interactions of these strings, could be picked up by advanced observatories like LIGO or future space-based detectors. The discovery of cosmic strings in M13 would not only confirm a long-standing theoretical prediction, but also revolutionize our understanding of the universe's structure and evolution. It would challenge our current models of cosmology, forcing us to rethink how matter and energy interacted in the universe's infancy. While the existence of cosmic strings remains unproven, the Hercules cluster serves as a promising candidate for further investigation, inviting astronomers to explore the boundaries of what we know and what we have yet to discover. By continuing to probe M13, we may uncover evidence of these elusive cosmic threads, unraveling yet another mystery of the cosmos and bringing us closer to understanding the grand tapestry of the universe. Now shifting our gaze to another cosmic marvel, we arrive at Messier 3 or M3, where astronomers have uncovered a stunning and puzzling feature, a mysterious blue ring of stars. This striking phenomenon defies expectations, as blue stars are typically young and hot, often found in regions of active star formation. Yet M3 is a globular cluster, a dense collection of ancient stars. So, what could explain this rare blue ring? One theory suggests that these blue stars might be the result of stellar collisions or interactions within the cluster. When stars pass too close to each other, their outer layers can merge, creating a new, hotter star that appears blue. Another possibility is that these stars are blue stragglers, stars that appear younger and bluer than their neighbors due to processes like mass transfer from a companion star. This phenomenon, while rare, offers a fascinating glimpse into the dynamic and sometimes chaotic nature of star clusters. The blue ring in M3 not only challenges our understanding of stellar evolution, but also highlights the unexpected beauty and complexity of the cosmos. As researchers continue to study this enigma, they hope to uncover the precise mechanisms behind its formation, shedding light on the intricate dance of stars within globular clusters. This discovery reminds us that even in the oldest corners of the universe, there are still mysteries waiting to be unraveled. Next, as we delve deeper into the wonders of star clusters, we'll explore another unexpected finding: the presence of heavy elements in the Sculptor cluster. Now shifting our focus to another cosmic puzzle, we turn our attention to the Sculptor cluster, where astronomers have made an unexpected discovery: the surprising presence of heavy elements. Typically, older star clusters like Sculptor are thought to be composed mainly of lighter elements such as hydrogen and helium, formed in the early stages of the universe. However, the detection of heavier elements like iron, nickel, and even gold in this cluster has left scientists intrigued. So, how did these metals find their way into such an ancient environment? One leading theory suggests that these elements were forged in the cores of massive stars and dispersed into the cluster through supernova explosions. When these stars reach the end of their lives, they explode in spectacular fashion, scattering their enriched material into space. Over time, this material can be incorporated into other stars or planetary systems within the cluster. Another possibility is that the Sculptor cluster may have interacted with younger, metal-rich galaxies, sweeping up these elements in the process. The presence of heavy elements in the Sculptor cluster challenges traditional views of stellar evolution, suggesting that even in the oldest regions of the universe, complex chemical processes are at work. This discovery not only deepens our understanding of how elements are distributed across the cosmos, but also highlights the interconnected nature of star formation and galactic evolution. As researchers continue to study this phenomenon, they hope to unlock more secrets about the life cycles of stars and the origins of the elements that make up our universe. Next, we'll venture into another fascinating discovery, the remnants of ancient supernova in M5. Now stepping into the realm of celestial echoes, we explore the remnants of ancient supernova within the M5 star cluster. These ghostly traces left behind by massive stellar explosions offer a unique window into the cluster's turbulent past. M5, one of the oldest and most densely packed globular clusters in our galaxy, holds secrets that astronomers are only beginning to unravel. The remnants were detected through faint X-ray emissions and the presence of shock-heated gas, which linger long after the explosive event. These signals serve as a cosmic fingerprint, revealing the energy and scale of the supernova that once lit up this cluster. But what makes these remnants particularly intriguing is what they tell us about M5's history. The distribution of these ancient echoes suggests that multiple supernovae occurred in relatively close succession, painting a picture of a cluster teeming with massive stars in its early days. This challenges the conventional view that globular clusters are composed primarily of low-mass stars. The presence of these supernova remnants also hints at the cluster's chemical evolution. The heavy elements forged in these explosions, such as iron and nickel, would have been scattered across the cluster, enriching its stars and potentially influencing the formation of new ones. This discovery sheds light on the dynamic processes that have shaped M5 over billions of years, offering a glimpse into the life and death of stars within one of the Milky Way's ancient treasures. Next, we'll uncover another mystery, the strange dimming of stars in NGC 6530. Now shifting our gaze to NGC 6530, we encounter a peculiar phenomenon that has puzzled astronomers, the strange and unexplained dimming of stars within this young cluster. Unlike other regions where stellar dimming follows predictable patterns, the stars here seem to flicker and fade in ways that defy conventional explanations. This cluster, located within the Lagoon Nebula, is a hotspot of star formation, brimming with young, hot stars. Yet, the erratic dimming observed raises questions about what might be causing this unusual behavior. One leading theory points to dense clouds of cosmic dust drifting through the cluster. These clouds could intermittently obscure the light from stars, creating the appearance of dimming. However, the irregularity of these events suggests that the dust might be unevenly distributed, adding another layer of mystery. Another possibility is that the stars themselves are undergoing unusual activity. Young stars, like those in NGC 6530, are known for their volatility, with intense magnetic fields and frequent flares. These outbursts could cause temporary dips in brightness, mimicking the effect of dimming. Some researchers have even speculated that the dimming could be linked to the presence of protoplanetary disks, rings of gas and dust surrounding young stars that could block light as they rotate. While these theories offer plausible explanations, none fully account for the observed patterns, leaving astronomers eager to uncover the true cause. This mystery not only challenges our understanding of stellar behavior, but but also highlights the complex and dynamic nature of young star clusters. As we move forward, our journey takes us to the synchronized movements of stars in M53, where another cosmic puzzle awaits. Now, as we delve into the cosmic ballet of M53, we witness stars moving in perfect harmony, as if choreographed by the universe itself. This globular cluster, nestled in the constellation Coma Berenices, is home to thousands of stars that appear to move in unison, a phenomenon that has captivated astronomers for decades. The synchronized motion of these stars is not just a beautiful spectacle, but also a key to understanding the intricate dynamics of star clusters. So, how does this cosmic dance occur? It all comes down to gravity. In a densely packed cluster like M53, the gravitational pull between stars creates a stable environment where they orbit the cluster's center in a coordinated manner. This gravitational harmony ensures that the stars move together, almost like a flock of birds in formation, but the implications go beyond the visual appeal. This synchronized movement provides clues about the cluster's history and structure. For instance, the uniformity of motion suggests that M53 has remained relatively undisturbed by external forces, preserving its original dynamics over billions of years. It also hints at the absence of massive disruptions, such as collisions with other clusters or the gravitational influence of nearby galaxies. Understanding this dance helps astronomers piece together the life cycles of globular clusters and how they evolve over time. It's a reminder that even in the vast expanse of space, there's an underlying order and rhythm, a delicate balance that keeps the stars in step. As we continue our journey, we'll uncover another fascinating mystery, the discrepancy in the mass of NGC 2808, where the numbers just don't add up. Now turning to a puzzle that has left astronomers scratching their heads, let's uncover the mystery of the missing stellar mass in NGC 2808. This globular cluster, located in the constellation Carina, has presented a baffling discrepancy. The mass calculated from its stars doesn't match the mass inferred from its gravitational effects. In simpler terms, the numbers just don't add up. So, what could be causing this cosmic mismatch? One leading theory points to the possible presence of dark matter. Although globular clusters are typically thought to contain little to no dark matter, NGC 2808 might be an exception. If dark matter is indeed lurking within the cluster, it could explain the extra gravitational pull that's unaccounted for by the visible stars. Another possibility is the presence of unseen stellar remnants, such as black holes or neutron stars, which could contribute to the cluster's mass without being directly observable. Alternatively, the discrepancy might stem from observational errors. Calculating the mass of a star cluster is no easy task, and even slight miscalculations in the distances, brightness, or motions of its stars could lead to significant errors. Advanced telescopes and improved data analysis techniques are helping astronomers refine their measurements, but the mystery remains unresolved for now. This enigma not only challenges our understanding of NGC 2808, but also raises broader questions about the nature of globular clusters and the role of dark matter in the universe. As we piece together the clues, we're reminded that even in the most well-studied corners of space, surprises are always lurking. Next, we'll explore another cosmic oddity, the mysterious gamma rays emanating from Terzan 5. Now shifting our focus to another cosmic enigma, let's unravel the mystery of the strange gamma rays coming from Terzan 5. This globular cluster, located in the constellation Sagittarius, has been emitting high-energy gamma rays that defy easy explanation. Gamma rays are the most energetic form of light in the universe, and their presence in Terzan 5 has sparked intense curiosity among astronomers. So, what could be producing these powerful emissions? One leading theory points to pulsars, the rapidly spinning neutron stars left behind after supernova explosions. Pulsars emit beams of radiation, including gamma rays, as they rotate, and Terzan 5 is known to host a significant number of these exotic objects. The combined emissions from multiple pulsars could account for the gamma rays observed in the cluster. Another possibility involves black holes. In particular, the interaction between stellar mass black holes and their surroundings could generate gamma ray emissions. These black holes, formed from the collapse of massive stars, might be accreting matter or colliding with other objects, releasing bursts of gamma radiation in the process. Additionally, some scientists speculate that the gamma rays could originate from more exotic phenomena, such as the annihilation of dark matter particles. While dark matter itself is invisible, its interactions could produce detectable gamma rays as a byproduct. However, this theory remains speculative, and further observations are needed to confirm it. The gamma rays from Terzan 5 not only challenge our understanding of globular clusters, but also provide a unique window into the high-energy processes at work in the universe. As we continue to study this cluster, we're reminded once again of the endless mysteries that await us in the cosmos. Next, we'll delve into the unusual orbits of stars in NGC 6101, another fascinating puzzle in the realm of star clusters. Now shifting our gaze to another celestial puzzle, we find ourselves examining the peculiar orbits of stars in NGC 6101. This globular cluster, nestled in the constellation Hyades, presents a captivating mystery with stars that follow paths unlike those typically observed in such clusters. Normally, stars in globular clusters move in predictable, almost circular orbits around the cluster's center, held together by gravity. However, in NGC 6101, many stars trace elongated, eccentric paths defying this norm. So, what could be causing these unusual orbits? One leading theory suggests that the cluster may have undergone a close encounter with another massive object, such as a dwarf galaxy or a large molecular cloud. Such an interaction could have disrupted the gravitational balance, sending stars into these strange trajectories. Another possibility points to the cluster's history of formation. NGC 6101 might have been born in an environment rich with chaotic gravitational forces, leading to the irregular orbits we see today. This unique behavior offers astronomers a rare opportunity to study the forces that shape star clusters over vast cosmic timescales. By analyzing these orbits, scientists can piece together the cluster's past and gain insights into the conditions that prevailed during its formation. The strange orbits of stars in NGC 6101 not only highlight the dynamic nature of globular clusters, but also remind us of the complex interplay of forces that govern the cosmos. Next, we'll explore the unexpected radio waves emanating from M22, another intriguing discovery in the world of star clusters. Now turning to another fascinating enigma, we delve into the unexpected radio waves detected from M22, a globular cluster located in the constellation Sagittarius. Radio waves are not typically associated with globular clusters, which are usually quiet in this part of the electromagnetic spectrum. However, M22 has defied expectations, emitting signals that have puzzled astronomers. So, what could be the source of these unusual radio waves? One leading hypothesis points to neutron stars, the dense remnants of massive stars that have exploded as supernova. Neutron stars can emit powerful beams of radio waves, especially if they are pulsars, spinning rapidly and sending out regular pulses of radiation. Another possibility involves white dwarfs, the remnants of smaller stars that have exhausted their nuclear fuel. In certain conditions, white dwarfs can produce radio emissions, particularly if they are in binary systems where material is being transferred between stars. These signals could also be linked to other exotic objects, such as black holes or even interactions between stars within the cluster. The discovery of radio waves in M22 opens up new avenues for understanding the dynamic processes at work within globular clusters. By studying these signals, astronomers can gain insights into the life cycles of stars, the behavior of dense stellar environments, and the mechanisms that drive cosmic phenomena. This unexpected discovery reminds us that even well-studied objects like M22 can still hold secrets waiting to be uncovered. Next, we'll uncover the hidden black hole lurking within NGC 3201, another intriguing revelation in the realm of star clusters. Now shifting our gaze to another cosmic conundrum, we explore the unexpected discovery of a hidden black hole in NGC 3201, a globular cluster in the constellation Vela. Black holes in globular clusters are rare, as these dense stellar systems are typically home to older stars and compact remnants like white dwarfs and neutron stars. Yet, NGC 3201 has revealed a surprising inhabitant. This black hole was detected through careful observation of the motions of stars within the cluster. Astronomers noticed that one star was wobbling in a peculiar way, as if it were orbiting an invisible companion. Further analysis confirmed that this unseen object had a mass around 4 times that of the Sun, strongly suggesting it was a black hole. What makes this discovery so intriguing is that it challenges our understanding of globular clusters. These clusters are thought to be inhospitable to black holes due to the intense gravitational interactions between stars, which often eject heavier objects like black holes from the system. Yet, this black hole has managed to remain, raising questions about how it formed and how it has survived in such a dynamic environment. One theory suggests it could be the remnant of a binary system, where one star collapsed into a black hole while the other remained intact. Another possibility is that it formed through the merger of smaller black holes within the cluster. This discovery not only adds to the growing evidence of black holes in globular clusters, but also provides a unique opportunity to study these mysterious objects in a densely populated stellar environment. As we continue to uncover the secrets of NGC 3201, we gain deeper insights into the complex and often unpredictable nature of star clusters. Next, we'll witness the cosmic fireworks lighting up the Eagle Nebula cluster, another spectacular phenomenon in the vast expanse of space. Now turning to a celestial spectacle that lights up the cosmos with unmatched brilliance, we explore the Eagle Nebula cluster, home to some of the most explosive stellar activity ever observed. Known as cosmic fireworks, these events are a breathtaking display of energy and creation. At the heart of this phenomenon lies the Eagle Nebula itself, a vast region of gas and dust where new stars are born. The cluster's most famous feature, the Pillars of Creation, towers over this stellar nursery, but it's the violent and dynamic processes within that truly captivate astronomers. Massive stars in this cluster burn brightly and fiercely, reaching the end of their lifespans in spectacular fashion. Supernova, the explosive deaths of these massive stars, scatter elements like carbon, oxygen, and iron across the cosmos, seeding future generations of stars and planets. These explosions also trigger shock waves that compress nearby gas, igniting the birth of new stars in a continuous cycle of creation and destruction. What makes this cluster particularly fascinating is the sheer scale of activity. Entire regions of the nebula are lit up by the intense radiation from young, hot stars, while others are shaped by the powerful winds and jets emitted by these stellar giants. This interplay of forces creates a dynamic and ever-changing environment, offering a front-row seat to the processes that shape galaxies. The significance of the Eagle Nebula cluster extends beyond its beauty. By studying this cluster, astronomers gain insights into the life cycles of stars, the formation of planetary systems, and the chemical enrichment of the universe. It's a reminder that even in the vastness of space, destruction often paves the way for new beginnings. Next, we'll uncover the unexpected presence of dust in the Lagoon cluster, adding another layer to our understanding of these stellar communities. Now shifting our gaze to another cosmic wonder, let's dive into the Lagoon cluster known as Messier 8, where an unexpected discovery has left astronomers intrigued. Mysterious dust. This vast star cluster, located in the constellation Sagittarius, is a bustling hub of stellar activity, but its dusty nature has raised questions. Typically, star clusters like Messier 8 are expected to be relatively dust-free, especially as they age, since intense radiation from young stars tends to blow away any residual material. Yet the Lagoon cluster defies this expectation. Here, clouds of dust persist, weaving through the cluster and creating a striking contrast against the bright young stars. But where does this dust come from? One theory suggests it might be the remnants of older stars that have reached the end of their lives. As these stars shed their outer layers, they release particles that linger in the cluster, creating the dusty veil we observe today. Another possibility is that the dust is being replenished by ongoing star formation within the cluster itself. When new stars are born, they often form within dense clouds of gas and dust, and the Lagoon cluster's active star-forming regions could be contributing to this ongoing supply. The presence of this dust is more than just a visual curiosity. It plays a crucial role in the cluster's dynamics. Dust can act as a catalyst for star formation, providing the raw material needed to create new stars. It also absorbs and scatters light, influencing how we perceive the cluster and its stars. By studying this dust, astronomers can gain deeper insights into the processes that drive star formation and evolution in such environments. The Lagoon cluster serves as a reminder that even in the seemingly chaotic cosmos, there's a delicate balance at play, one where dust, stars, and the forces of nature intertwine to shape the universe as we know it. Next, we'll explore the unusual pulsating stars in Messier 71, adding yet another fascinating layer to our journey through these stellar mysteries. Now turning to the intriguing world of Messier 71, a globular cluster in the constellation Sagittarius, we encounter stars that seem to dance to their own rhythm. These are pulsating stars, and their unusual behavior has captivated astronomers for decades. Unlike typical stars which shine with a steady light, these stars expand and contract, causing their brightness to fluctuate in regular patterns. This phenomenon, known as stellar pulsation, occurs when the star's outer layers trap and release energy in a cyclical manner. For stars in Messier 71, this pulsation is particularly fascinating because it challenges our understanding of how stars evolve in tight-knit clusters. So, what causes these pulsations? The key lies in the internal structure of the stars themselves. In the dense environment of a globular cluster, stars often interact gravitationally, which can alter their internal dynamics. For some stars, this leads to instability in their outer layers, triggering the pulsations we observe. Additionally, the advanced age of stars in Messier 71 plays a role. Older stars have undergone significant changes in their cores, and these changes can cause their outer layers to become unstable, leading to the rhythmic expansion and contraction we see. But the implications of these pulsations go far beyond their mesmerizing light show. By studying these stars, astronomers can gain valuable insights into the internal workings of stellar processes. Pulsations act like a cosmic stethoscope, allowing scientists to probe the internal structure and composition of stars. This information helps refine models of stellar evolution, particularly in the context of globular clusters where stars are densely packed and interactions are frequent. Moreover, the pulsating stars in Messier 71 provide clues about the cluster's history. The frequency and intensity of the pulsations can reveal details about the star's ages, masses, and chemical compositions. This data, in turn, helps piece together the cluster's formation and evolution over billions of years. It's a reminder that even the smallest changes in a star's behavior can unlock vast cosmic secrets. As we move forward, our journey through the mysteries of star clusters continues with another remarkable discovery in Messier 16, also known as the Eagle Nebula Cluster. Here, we'll explore the surprising spread of ages among its stars and what it tells us about the process of star formation. Stay tuned as we unravel more of the universe's stellar enigmas. Now shifting our gaze to the intriguing case of NGC 104, also known as the Great Globular Cluster 47 Tucanae, we stumble upon a cosmic mystery, the surprising absence of planets. In most star clusters, planets are expected to form alongside stars, but NGC 104 defies this expectation. Despite its dense population of stars, this cluster appears to be nearly devoid of planets, leaving astronomers puzzled. So, why are planets so rare in this cluster? One leading theory points to the intense gravitational interactions caused by tidal forces. In a tightly packed cluster like NGC 104, stars are in constant close proximity, and their gravitational pull can disrupt planet-forming disks. These tidal forces may rip apart nascent planets or scatter them into the void of space before they can fully form. Additionally, the frequent close encounters between stars in such a dense environment could destabilize or eject existing planetary systems, leaving behind a barren stellar landscape. Another possibility lies in the cluster's age and composition. NGC 104 is one of the oldest known globular clusters, with stars that formed billions of years ago. At that time, the universe had fewer heavy elements which are essential for building planets. Without an abundance of these materials, planet formation may have been far less likely in this cluster compared to younger, metal-rich regions of space. Despite the apparent absence of planets, studying NGC 104 offers valuable insights. It challenges our assumptions about where and how planets can form and highlights the dramatic influence of environment on planetary systems. As we continue to explore the universe, clusters like this remind us that the cosmos is full of surprises, each one deepening our understanding of the intricate dance between stars, planets, and their surroundings. As we look ahead, our journey takes us to the Trifid Nebula Cluster, where sudden and mysterious flares have captured the attention of astronomers. Stay with us as we uncover the secrets behind these cosmic bursts and what they reveal about the dynamic nature of star clusters. Now turning our attention to the Trifid Nebula Cluster, we encounter a phenomenon that has left astronomers both fascinated and puzzled: the sudden and mysterious flares that light up this stellar nursery. These bursts of energy appear without warning, illuminating the surrounding gas and dust with an intensity that defies easy explanation. What could be causing these dramatic cosmic events? One leading theory suggests that these flares are the result of stellar collisions. In a crowded cluster like the Trifid Nebula, stars often wander perilously close to one another. When two stars collide or come into close contact, the energy released can produce a spectacular flare visible across vast distances. Such collisions are rare, but in a densely populated cluster, they become more likely, offering a plausible explanation for these sudden bursts of light. Another possibility points to the power of magnetic fields. Some stars in the Trifid Nebula Cluster may possess incredibly strong magnetic activity, capable of triggering massive flares similar to those seen on our own sun, but on a much grander scale. These magnetic interactions could cause violent outbursts of energy, ejecting material into space and creating the luminous flares observed by astronomers. This process, known as magnetic reconnection, is a well-documented phenomenon but remains challenging to fully understand in the context of star clusters. There's also the intriguing idea that these flares could be linked to the birth of new stars. As young stars form, they often go through periods of intense activity, ejecting jets of material and emitting powerful bursts of radiation. These stellar tantrums could be responsible for the flares, marking the tumultuous early stages of a star's life. Whatever the cause, the flares in the Trifid Nebula Cluster offer a glimpse into the dynamic and often chaotic nature of star formation. They remind us that even in the seemingly serene depths of space, energy and matter are in constant flux, creating phenomena that challenge our understanding and inspire further exploration. With this mystery still unfolding, we now move to the Eagle Nebula Cluster, where an unexpected spread in stellar ages awaits our investigation. What does this diversity of ages tell us about the process of star formation? Join us as we delve into this cosmic enigma, as we shift our focus to the Eagle Nebula Cluster, also known as M16. We uncover a discovery that challenges our understanding of star formation. Here, astronomers have observed a surprising spread in the ages of stars, a finding that defies the conventional idea that stars in a cluster form around the same time. This unexpected diversity raises fascinating questions about how and when stars come into existence. Typically, star clusters are thought to be born from a single, massive cloud of gas and dust, with most stars forming in a relatively short period, astronomically speaking. However, in the Eagle Nebula Cluster, this isn't the case. Observations reveal stars ranging from mere infants, just a few million years old, to older stars that have been shining for tens of millions of years. This age gap suggests that star formation in this region has been an ongoing process, occurring in multiple waves rather than a single burst. So, what could explain this prolonged period of star birth? One possibility is that the Eagle Nebula's environment is exceptionally dynamic. Turbulent interactions within the gas and dust, triggered by supernova explosions or collisions with other clouds, could have reignited the star-forming process multiple times over millions of years. Each wave of star formation would then produce new generations of stars, creating the diverse age range we see today. Another theory points to the role of massive stars in shaping their surroundings. These stars, with their intense radiation and powerful stellar winds, can compress nearby gas, triggering the birth of new stars even as older ones continue to evolve. This process, known as triggered star formation, could explain how the Eagle Nebula Cluster sustains its active and varied stellar population. This discovery has significant implications for our understanding of star formation. It suggests that clusters can be more complex and varied than previously thought, with star birth occurring over extended periods rather than in a single, brief event. The Eagle Nebula Cluster serves as a reminder that the universe is full of surprises, constantly challenging our assumptions and deepening our knowledge. As we continue to explore the mysteries of star clusters, our journey takes us next to the strange shadows observed in NGC 2264. What do these cosmic silhouettes reveal about the structure and history of this cluster? Let's find out together. Now, as we turn our gaze to NGC 2264, we encounter a phenomenon that seems almost otherworldly. Here, astronomers have observed strange, shadowy structures weaving through the cluster, casting cosmic silhouettes that hint at a deeper story. These shadows, though mysterious, offer intriguing clues about the cluster's structure and history. At first glance, these shadows might appear to be mere voids or gaps in the cluster's stellar population. However, closer examination reveals that they are actually dense regions of gas and dust, acting like cosmic curtains that block the light from stars behind them. These shadowy patches are not random but are shaped by the cluster's internal dynamics, including the gravitational pull of stars and the movement of material within the cluster. One of the most striking features of these shadows is their intricate shapes. Some appear as long, wispy tendrils, while others form dense, irregular clumps. These formations suggest that the gas and dust in NGC 2264 are being shaped by powerful forces, such as the stellar winds from massive stars or the shock waves from past supernova explosions. These forces compress and sculpt the material, creating the shadowy patterns we observe today. But what do these shadows reveal about the cluster's structure? For one, they indicate that NGC 2264 is still an active and dynamic environment, where gas and dust play a crucial role in shaping its evolution. The presence of these shadows also suggests that the cluster is relatively young, as older clusters tend to have cleared out much of their primordial gas and dust. This means that NGC 2264 is still in the process of forming stars, with these shadowy regions potentially serving as nurseries for new stellar generations. Another fascinating aspect is how these shadows interact with the cluster's light. The way they absorb and scatter starlight can provide astronomers with valuable information about the composition and density of the gas and dust, offering insights into the conditions necessary for star formation. By studying these shadows, scientists can piece together a clearer picture of how stars are born and how clusters evolve over time. As we delve deeper into the mysteries of NGC 2264, these cosmic shadows remind us of the complexity and beauty of the universe. They are not just dark patches but windows into the inner workings of a star cluster, revealing the forces that shape its destiny. And with that, our exploration continues as we move to the puzzling absence of neutron stars in M12, a discovery that challenges our understanding of stellar remnants. Stay with us as we uncover more cosmic secrets. Now, shifting our focus to M12, we encounter one of the more perplexing mysteries in the realm of star clusters, the puzzling absence of neutron stars. Neutron stars, the incredibly dense remnants of supernova explosions, are typically expected to be present in globular clusters like M12. Yet, despite extensive observations, they seem to be missing, leaving astronomers with a cosmic puzzle to solve. One theory suggests that these neutron stars may have been ejected from the cluster due to intense gravitational interactions. In a dense environment like M12, stars often pass close to one another, and these close encounters can lead to dramatic changes in their trajectories. A neutron star, with its immense gravitational pull, could be flung out of the cluster entirely if it experiences a strong enough gravitational kick. This process, known as dynamical ejection, could explain why we're not detecting them within the cluster's boundaries. Another possibility is that the neutron stars are still there, but they're simply invisible to our current observational methods. Neutron stars emit most of their radiation in the form of X-rays or radio waves rather than visible light. If these emissions are too faint or if the neutron stars are not actively pulsing, they could easily evade detection. Additionally, the dense core of M12 might be obscuring our view, making it difficult to spot these elusive objects even if they are present. Some researchers have also proposed that the absence of neutron stars could be linked to the cluster's unique history. If M12 experienced a period of intense stellar collisions or interactions in the past, it's possible that many of its neutron stars were destroyed or merged with other objects. Alternatively, the cluster's formation process might have been different from others, resulting in fewer neutron stars from the outset. The mystery of the missing neutron stars in M12 challenges our understanding of how these dense remnants behave in star clusters. It also highlights the limitations of our current observational tools and the need for more advanced technology to uncover these hidden cosmic secrets. As we continue to study M12, this enigma reminds us that even in the well-studied corners of the universe, there are still surprises waiting to be discovered. And with that, our journey takes us to the next discovery, the mysterious alignment of planets in M4, a phenomenon that defies our expectations of planetary systems. As we venture deeper into the cosmos, our next stop brings us to M4, a globular cluster that harbors a truly baffling discovery, the unexpected alignment of planets. Planetary systems, as we understand them, are usually believed to form in a somewhat chaotic and random fashion, with planets orbiting their stars in various orientations. However, in M4, astronomers have detected planets that appear to be aligned in a way that defies this expectation, raising questions about how such a phenomenon could occur. The alignment in M4 suggests that these planets share a common orientation, as if they were all influenced by the same force or process during their formation. This is particularly unusual because globular clusters like M4 are densely packed with stars, creating a dynamic environment where gravitational interactions are constant. One theory proposes that the cluster's strong gravitational field may have played a role in shaping the planetary systems, aligning them over time through tidal forces. Another possibility is that the alignment is a remnant of the cluster's early history, where conditions during planet formation were markedly different from those in less dense stellar environments. This discovery challenges our understanding of how planetary systems form and evolve, especially in extreme environments like globular clusters. It also raises intriguing questions about the stability of such aligned systems. Could this alignment persist over billions of years, or would it be disrupted by the cluster's chaotic dynamics? Understanding this phenomenon could provide new insights into the diversity of planetary systems across the universe and the conditions that allow them to exist. The mysterious alignment in M4 also underscores the importance of studying globular clusters as laboratories for planetary science. These ancient clusters, with their unique environments, offer a window into processes that are rarely seen elsewhere. As we continue to explore M4 and other clusters, discoveries like this remind us that the universe is full of surprises, constantly challenging our assumptions and expanding our knowledge. And with that, we set our sights on the Jewel Box Cluster, where another cosmic enigma awaits. Now shifting our gaze to the Jewel Box Cluster, we uncover another cosmic mystery, its strange and unusual chemistry. Officially known as NGC 4755, this cluster is not only visually stunning but also chemically intriguing. Astronomers have detected unexpected elements and compounds within its stars, raising questions about how such a diverse chemical composition could have formed. This discovery challenges our understanding of stellar evolution and the processes that shape star clusters. One of the most striking features of the Jewel Box Cluster is the presence of heavy elements such as iron and magnesium in quantities that don't align with typical stellar evolution models. These elements are usually produced in the cores of massive stars and dispersed into space during supernova explosions. However, the Jewel Box Cluster's stars appear to have acquired these elements in a way that defies conventional explanations. Some theories suggest that the cluster may have experienced multiple waves of star formation, with later generations of stars incorporating material from earlier supernova. Another puzzling aspect is the variation in chemical signatures among the cluster's stars. While most stars in a cluster are expected to share a similar composition due to their common origin, the Jewel Box Cluster shows significant differences. This could indicate that the cluster's environment was unusually turbulent, allowing for a mix of materials from different sources. Alternatively, it might suggest that some stars interacted with passing gas clouds or even with each other, altering their chemical makeup over time. The strange chemistry of the Jewel Box Cluster has broader implications for our understanding of the universe. It highlights the complexity of star formation and evolution, particularly in dense and dynamic environments. By studying clusters like this, astronomers can gain insights into how elements are distributed across the cosmos and how they contribute to the formation of new stars and planets. As we ponder the Jewel Box Cluster's chemical enigma, we are reminded once again of the universe's ability to surprise and challenge us. With every discovery, we uncover more questions, pushing the boundaries of our knowledge and inspiring further exploration. Now we turn our attention to the faint, ghostly light surrounding Omega Centauri, where another mystery awaits. Now shifting our focus to Omega Centauri, also known as NGC 5139, we encounter another celestial enigma, the faint, ghostly light that surrounds this massive globular cluster. This mysterious glow has puzzled astronomers for years, as it doesn't seem to originate from the cluster's stars alone. Instead, it appears to permeate the space around them, creating an eerie and unexplained halo. One theory suggests that this faint light could be the collective glow of ancient stars, remnants from the cluster's earliest days. These stars, now dim and barely detectable, might have been pushed to the outskirts of the cluster over billions of years, leaving behind a faint trace of their presence. Another possibility is that the light comes from rogue stars, those that were ejected from the cluster due to gravitational interactions and now wander the surrounding space, emitting a faint glow. However, the most intriguing explanation involves dark matter. While globular clusters like Omega Centauri are typically thought to contain little to no dark matter, the presence of this ghostly light could hint at a hidden reservoir. Dark matter, which does not emit light but exerts gravitational influence, might be interacting with the cluster's stars and gas in a way that produces this faint emission. If confirmed, this would challenge our understanding of how dark matter is distributed in the universe, particularly in dense stellar environments. The ghostly light also raises questions about the history and evolution of Omega Centauri. Could it be the remnants of a smaller cluster that merged with Omega Centauri long ago, leaving behind a faint trace? Or does it point to a more complex process of star formation and dispersal within the cluster itself? As we explore this phenomenon, we're reminded once again of the universe's ability to conceal secrets in plain sight. The faint glow around Omega Centauri may seem subtle, but it opens up profound questions about the nature of star clusters, the role of dark matter, and the intricate processes that shape our cosmos. With this mystery still unfolding, we turn our attention to the next discovery, where the universe continues to reveal its wonders.